Hello, everyone, and welcome back to chapter 6, and where here we will be talking about energy and metabolism. So, energy and metabolism is one of those kind of key characteristics of living organisms. For us to be considered living, we need to actually, utilize energy and metabolize products, and of course, which all requires energy. So, just for example, here we see this lion devouring a whole giraffe. As gruesome as that might look like, that's the circle of life, and that's how this lion is able to, be able to live because it's actually, taking the energy from the giraffe and taking it into himself. So then, so he could use that energy later on by running or other work. So let's now dig in. So let's talk about, specifically thermodynamics. As we all know, is that biology is a multidisciplinary uh, field. So by multidisciplinary field, I mean that it actually is a field that is not just governed just by biology, but it's also governed by chemistry and physics. So where you have multiple fields coming in together. And an example for where biology you can see this in biology is in thermodynamics. Thermodynamics is a branch of chemistry that is concerned with energy changes. So thermo is actually heat. Dynamics is just the changes. As we know, heat is a form of energy. So hence that's where thermodynamics comes from. So if you ever want to actually understand thermodynamics, what it means, just think about the word thermodynamic. Thermo heat, so energy, dynamics changes. So it's literally, heat changes or energy changes. That's what, thermodynamics is. And thermodynamics, this thing is actually, very, you see this in your cell because there's a lot of energy changes that are occurring in the cell. Cells are constantly breaking molecules, making new compounds, and massive macromolecules. Everything needs energy. Energy is being literally kind of used up there and there to create other molecules, to break down molecules, and it's being conserved in certain areas to keep it, to store it. So there's always this changes of energy. So as we look at the cells, as we know, they are governed by the laws of biology, but they're also, governed by laws of physics and chemistry, and specifically here the thermodynamics. So we're going to go a bit more details. So this kind of chapter is, of course, is under biology, but there's a lot of chemistry and physics laws that you guys need to know. So we're going to go through them bit by bit. So let's talk about energy. What is energy? Well, energy, if you really want to define it, it's the capacity to do work. This is what energy is. It's just the ability for something to do work. And this can come in two states. It can come in kinetic and potential. So let's talk about kinetic. The name kinetic already should be self-explanatory. Kinetic is anything that's moving. So it's energy in an object that's moving. That object could be, for example, a ball that is literally rolling down. Well, that ball is in motion. All the energy in that ball is called kinetic energy because that ball is moving. However, if that basically, ball, goes into the cliff and is literally at the point of the cliff, like really up the top, and is just there standing. It's not moving, but it has the ability to later actually fall down again and do work. That's called potential. So it's literally when that ball is at in a rest state, but it has the ability to do work. So its energy is stored. It's called stored energy. So it's stored there and it's stored until kinetic energy goes again. So let's give you here an example. So you have basically this little kid that is going, in this way, basically up here. I'm trying to find the name for this, but anyway. So she goes up the ladder and she sits up top. When she just sits there and she doesn't move, that's potential energy because the energy that she's not moving, there's no energy being done, but she's sitting there and they're basically she can go down the slide. That's the name. I finally got it. It's the slide. So she's sitting on the top of the slide, and nothing can happen. She's just there, and technically, if she wants, she could push herself then down, and that could be converted into kinetic. But at that point where she's just standing there, that's potential energy because there's a potential, there's a probability that the G might do some energy. So all the energy that's it's there is called potential. When she slides down, that's then kinetic because now she's moving. So that's the difference between potential and kinetic. Potential is you're literally, there is this possibility for you to do work. There's the capacity of it, but you're still in, your energy stored because you're not moving. But there's the capacity. There might be, a chance of you doing that energy. So your energy is stored as potential energy. And then when it goes down, when you're in motion, it's transferred from potential to kinetic. So that energy is suddenly not stored, it's being released to give you that kinetic energy. And when you look at energy, energy can come in many, many forms. It can come in as mechanical, heat, sound, electric current, light, or radioactivity. These are all different types of energy that we can see. However, for us scientists, we like to really kind of look at energy as heat. And then you start questioning why. Why do we want to see, why, out of all these different forms of energy, why are we looking at an energy as heat? Simply because all of these types of forms of energy can be converted into heat. So that's why we really look into heat as energy, because radioactivity can be converted into heat, same as light, same as the current, same as the electric current, sound or mechanical. We can convert that into heat. So that's why we use calories then to measure heat. Because if we take a look at a calorie is what is basically the heat required to raise 1 gram of water. That's 1 calorie. So for us, that the most convenient way to measure energy is heat, because basically all these different types of energies you can convert them to heat. So you can measure basically calories, which is a form of energy and heat. So again, we know this from before. 1 calorie is heat required to raise 1 gram of water by 1 Celsius. That's what it literally is. So you see this a lot actually in your food labels. So if you go actually, buy any product from the supermarket and you basically go on one of the sides and you see your dietary information, it should tell you there, for example, how many calories. And those calories are just how much energy does this food have in the form of heat. So that's what it means, the calories is the form of heat. And most of the time you see it in kilocalories, so kc, which is literally basically, it's just 1 calorie is one, sorry, a kilocalorie is 1,000 calories. So that's why the kilo is just 1,000. That's what it means. So that's energy. So now let's talk about the energy flow. So now, as we know, energy has to be flowed around, has to go from one state to another state. It needs to, travel to different organisms or different objects. Well, the main source of energy, if you think about it, it comes from this big, beautiful ball that's just, burning up in the sky, which we like to call the sun. That's where we actually get most of our energy. So if you look at the biological world, so like plants, bacteria, all these kind of different organisms, they are able to convert energy from the sun, so the heat from the sun, into molecules, hence photosynthesis. They're able to actually take in the sunlight, a bigger CO2, and they're able then to break bonds, break, the energy, use the energy from the sunlight, break CO2, and create these carbon structures, these kind of, let's say, sugar molecules, which have a lot of energy stored into them. So that's where they get their energies from the sun. And this sun is really helping them to actually use all these energies. Because what it does, for example, is that you have, this energy as a in some sort of way like this form of heat. So the plant is going to take that heat and it's going to take CO2 and it's going to store all of that basically heat energy into the chemical bonds that's going to be creating, the sugar compounds. So in photosynthesis, it's just taking literally the heat energy, taking CO2, building a carbon structure. So basically, this sugar molecule, and inside the sugar molecules, basically these kind of bonds, they have the energy stored there. So again, you get the plant, it's taking the energy as heat, and it's using the energy to break bonds, like from the CO2 from the environment. It's breaking bonds, breaking them, and you're creating now a sugar molecule. And all these new bonds that you created are basically storing the energy. So in this case, there's a lot of energy being used to break bonds, but a lot of it is then basically going back into creating new bonds. So when we look at bonds, when you look at basically molecule compounds or molecules, so again, molecules are atoms that are basically bound together, two or more atoms that are bound together. Compounds is the same thing, but they have to be different elements. Remember that. So when these basically compounds or molecules have these chemical bonds. These chemical bonds have the energy. It's literally inside there. And these are very important because when you break that bond, you can transfer it because, of course, you're breaking that bond that has a lot of energy. You break it, energy is going to flow. So the energy that's released can be transferred to somewhere else. And that's very important. And we'll definitely go into much more details about that. So let's give you an example here where you really do see this kind of storing of energy and then transferring that energy by breaking bonds. And that's in redox reactions. So if you guys remember, redox reactions are literally reactions in where you have a transfer of one or more electrons. So you basically have, in this case, for example, here, compound A is losing an electron. So as you can see here, from A to B, there's a transfer of electron. So A is losing an electron. So this guy's getting oxidized while B is gaining an electron. So that's that's called reducing. It's being reduced. Why do you think it's reduced even though it's gaining? Because it's gaining an electron. So it's gaining a reduction, so a negative. So that's why we call it a reduction. So you have A being the oxidized partner, B becoming your reduction. So again, oxidation is the atom or molecules loses an electron. Reduction is literally atom or molecule gaining an electron. So basically, when you have these, this is called when you have an oxidation and reduction reactions. It's called a redox. It's re for reduction and dox, and ox is for oxidation. So these reactions are always paired, meaning that when there's a transfer of electrons, this is a redox because one is being oxidized and one is reduced. However, this transfer of electron is literally you're breaking a bond there, and you're transferring that energy. So A now is breaking that bond, and that energy that's released is being transferred to B. So A now has less energy than before, and B has much more energy than before. So as you can see here, basically in this yellow, this is lower energy because it lost an electron. It broke that bond that has energy, and it broke it and it transferred it to B. And this is how chemical reactions occur when basically you have, let's say, reagents coming together and they're creating new products. There has to be breaking of bonds and creating new bonds. So some molecules are losing energy and other ones are gaining energy. That's literally chemistry in general. Anything that reacts, some energy is going to be basically lost and gained somewhere. And that's literally thermodynamics. That's the change of energy. And this is a pure example where now suddenly A has lost it and B has gained. This is literally chemistry and life, if you always want to put it in a chemical equation sometimes. So when it comes to thermodynamics, as we saw, that there's going to be a lot of changes in energy, right? So energy is going to be lost, energy is going to be created, a lot of things can happen. But there's laws that we started to see in thermodynamics in the changes of energy. There's two of them. There's the first law of thermodynamics and the second. So the first law, what it states is that energy cannot be created or destroyed. So that literally, if you want to put it in a more simpler version, energy, energy that's found in this world is constant. We cannot create it or we cannot destroy it. It's there constantly and we keep using it. We keep recycling it and it's going from one place to the other. We are not these superior beings that we can create energy. That is impossible. And we cannot get energy and we cannot destroy that energy. We cannot destroy heat. We cannot destroy sunlight. All these things, we're not able to do that. So that's the first law of dynamics. So that's why when it comes to thermodynamics, energy is not created or basically broken. It's transferred. So one molecule, or let's say one organism, is transferring its energy from one place to the other. And I'll give you here another example in real life. As human beings, we need energy, right? We need energy to study. You need energy right now to focus on my annoying voice. Well, how do you do that? Well, you need to get energy. You're not going to be able to create it. You're going to go and eat something, right? Let's imagine you go and eat a banana, or let's say meat. You go eat a steak. You eat the steak that's coming from a cow. Well, we're literally just taking the energy from the bonds in that steak because that steak has a lot of these chemical bonds. Well, we're gonna break them and take all the energy in there. Well, the same thing happened to the cow. The cow got its energy from literally what do you call it? Eating grass because the grass has now all these chemical bonds. Well, the cow's gonna just keep biting it, destroying those bonds and taking that energy into herself. So, and the plant, then where did the plant get its energy? From the sun. The sun is literally, you know, giving a lot of sunlight in form of energy, and it's using it to put it in its, carbon molecules, and creating these bonds with a high energy. So you see, there's no energy being created here. It's just a circle. It's literally just a circle that's going, and basically in this kind of in that direction. So energy here was never created and it was never destroyed. It was just going from one pole to the other. So from the sun to the plant to the cow to you. So energy there was never created and it was never destroyed. It was just being passed. That's the first law of thermodynamics. Hence, energy is constant in this universe. It remains constant. So now the second law of thermodynamics. This second law is a bit more tricky, and it's actually one of those laws that a lot of engineering students have been, kind of getting very confused with. And so what I've done, I've attached another video of, I think it's from Khan Academy. Khan Academy is an amazing, basically YouTube channel that really, it dives into almost every single aspect of science. So I put that to further explain to you second law of thermodynamics. So read from the textbook, listen to me in the lecture, and also from this video. And if you cannot understand it still, there's that extra video. And if that video doesn't help, please let me know, and I'll definitely have the time to explain it because it's not a very easy law sometimes to take into care. Because imagine even engineering students sometimes cannot understand it. So second law of thermodynamics, what it basically means is, so when we know as that energy is being, transferred, from one organism to A. So let's imagine organism A transfers basically energy to B. That transfer of energy is not 100%, meaning that when that energy is going from A to B, let's say 80% is going there, but that 20% is lost. That's basically the second law of thermodynamics, that not all energy is being transferred completely, and there's always going to be energy that's lost. And that energy that's lost, you cannot use it. It's unavailable energy. And that can be basically random motion of molecules. That can be an increased number of energy states or an increased dispersal of energy in the system. So this is what the unavailable energy means. Is basically some molecules can be just randomly leave. Some of them can just basically have an increased state. They use that extra energy that you're not able to use it and to give, let's say, this extra energy state. So this is in the K element, or basically it just disperses into another system. So that's this unavailable energy. And this unavailable energy, the thing that we cannot use, we like to call it as as randomness or disorder in the system. Just think about it. you know, you want to transfer energy from A to B. Well, this 80% that's being transferred is very organized energy. It's just very organized, it's going from one place to the other. Well, this other that's just really going, randomly, that's chaos. That's what we call literally randomness or disorder. And we can measure that with entropy. So that's S. So S is literally the measure of how much of this unavailable energy or this random or disorder of a system that there is. So entropy is literally, again, this unavailable energy or randomness. So if you think about randomness is this random motion of molecules or dispersion of energy in the system that's leaving that we cannot use. And if you want to think about this in a life sense thing, life is more random or chaotic than order. And I'll give you here an example. Let's imagine you get bricks. You go and you put the bricks, you put them in basically in a very nice kind of, let's say, you pile them up to create this, let's say, small little, I don't know, a block. You pile them up perfectly, organize them, so that's how they stay. A wind is suddenly going to blow them off and they're going to fall down. What's the probability of them to reconstruct spontaneously? 0%, right? There's no way in hell that these bricks are going to reorganize themselves to actually, create this nice layer or brick of layers. It's impossible because life always likes to be in chaos and randomness. That's his life, actually, if you think about it. So things, basically, objects always like to go from an ordered to a chaotic sense. They always like to. They don't like to go from chaos to order because it's quite impossible. Because think about it in the sense of like when you see chaotic bricks laying around, will they by themselves be ordered? No, not really. But think about this differently. If basically the bricks are organized, will they probably fall down and basically become much more, let's say, unorganized spontaneously? Yes, they can. Something can happen throughout time, but they're going to basically fall down spontaneously. So that's what it basically means here. So as you can see, any energy transformations process spontaneously to convert matter from a more ordered, less stable form to a less ordered, more stable form. So here what they're saying is that a ordered, less stable, so ordered is more organized, which is less stable because it will fall apart, into a less ordered, so more stable form. And let's use an example here of entropy when it comes to uh, ice. So let's imagine you have a water cup and you have ice. Ice is in a very ordered manner, right? Because basically it's literally these kind of water molecules that are ordered and put in this certain order to create this really nice lattice or this nice cube, which is then ice. So they're in a very ordered fashion. And you put this in room temperature, so 23 degrees. Well, what's going to happen is that these guys are going to go from a more ordered, less stable, to a less ordered, more stable form. And that is basically they're just becoming much more chaotic, more dispersed. These water are basically breaking down and they're just going different directions in a form of water. And that's hence the entropy in this ice cube is low because entropy measures randomness or chaos or this basically unavailable energy. Here, there's a lot of this available energy because it's so ordered. Well, when it starts to melt, the entropy increases because now the randomness, this unavailable energy that's gone or left because it's just literally, dispersing chaotically, is increasing. So hence, here the ice cube's entropy is is increasing when it melts. So the entropy here is much higher compared to here, because here the randomness is very low because it's very highly structured. So there is a lot of this available energy. But when it basically starts to disperse, you're losing all that available energy, and hence the entropy is increasing because now the randomness is just increasing because the water molecules are dispersing much more freely here in this water than inside that ice cube because that this is much more ordered and structured. So think that's how we have to think about entropy. So I'm gonna go one more time with this because it's very important. Second law of thermodynamics, it just focuses on the energy transfer efficiency. So how efficient is energy transfer from A to B? So energy is never gonna be transferred 100%, never. So there's always energy lost. That's gonna be randomly, dispersed. That is entropy. That is randomness disorder. Entropy is the amount of this random energy that's leaving, and that is unavailable energy. You cannot use that energy. You cannot transfer that energy. You cannot use that to work. So remember that. And basically, in general, life is chaotic. Life likes to always go from organized to chaos. So entropy in general always is increasing in life because to keep something very highly ordered takes a lot of energy. And which is very costly. You don't want that. So you rather go to a less ordered, so more stable kind of form because you don't need much energy for that. And that's why ice cubes they to keep ice cubes there, you need a lot of energy. So you need to put them in a freezer that says keep pushing so much energy to keep them cold. Normally, if you put them outside, they're gonna lose that energy because now suddenly, all this kind of organization is gonna leave because this chaos is gonna come. So this entropy is gonna increase, and this random unavailable available energy is gonna leave out, and that's why they actually melt. So now we spoke about the two laws of thermodynamics. So chemical reactions in this world, they need to follow that, meaning that they cannot create energy, they cannot destroy energy. Great. Second, chemical reactions cannot use basically all the energy available there because there's always some. entropy, some energy that we cannot be used, that cannot be used. Okay, great. So those are the two laws that chemical reactions need to follow. So one thing that we basically sometimes like to do is actually measure how much energy can we utilize then in a reaction, because we know some of it cannot be used, but how much of the energy can be used or can be transferred? And that's free energy. Is the energy available to do work, and we like to call that as G. So G is literally free energy, is the energy available to do work. So in a chemical reaction, how much of that energy that's being transferred can we use to do work? Because we know that there's some of it that's going to leave and we cannot use it. So there's a really beautiful equation for this where G is equal to H minus Ts. H is the enthalpy. H is the energy in the molecule's chemical bond. So how much does that molecule have in energy? Because as we said, all the energy is stored in chemical bonds. Okay, how much is there? Then subtract it by the absolute temperature, how much temperature there is, in the system, and S is the entropy. How much of that energy is unavailable? So again, let's imagine you have a compound in a system. That system is temperature basically constant and the pressure is constant. These are important because if temperature or pressure is not constant, this does not apply. So this equation only applies when temperature or pressure are actually equal, are basically constant. So let's go back to this again. Free energy, basically here, what you're trying to do is to see how much energy can you use to do work in this compound. So you look at this compound and then you look at how much enthalpy there is. So how much energy is in the chemical bonds. So you have this amount of energy, great. Then you subtract it by the absolute temperature. What's the temperature in the system? Because that energy you cannot use. And the S, which is the entropy, the unavailable energy. So then you subtract it from there. So you're subtracting basically the whole energy that's this molecule that's going to transfer, and then you subtract basically the thing that you cannot use. So hence you're just literally taking the energy available to do work. So this Ts is expressed as the amount of disorder in the system. So Ts literally is the absolute temperature and the entropy. Well, these guys is the amount of disorder in the system. This is the amount of energy that you cannot use. This is the unavailable energy in the system. So you subtract that unavailable energy from the whole energy that's actually found in the molecule's chemical bonds. So one more time, I'm going to explain this. You have a compound, like let's imagine you have glucose. Okay, you look at glucose, it's like how much of that energy can I use from glucose to do work? That's basically G. You want to see the free energy. Okay, great. How can we do that? Well, it's simple. You actually then take how much energy there's in the bonds, and that's enthalpy, so H. But I know from the second law of thermodynamics is that when I break these bonds and I want to transfer them somewhere else, I cannot use all the energy there. Some of it is going to be randomly distributed out. So I need to remove that because that is not energy that I can use. So then you subtract the absolute temperature, which is T, and then the entropy. So how much of that is basically unavailable to me? That's how you actually calculate it. So now let's go into change in free energy. So this comes more in when you have actually chemical reactions. So when you have, for example, products and sorry, what's it called, reagents and products. So I'm gonna hopefully try to find an example here. So chemical reactions. So for example here. So you have basically here, these are, CH4, and two O2s. And then basically you get two water molecules and carbon dioxide. So what happens here is that there's going to be changes in energy. So suddenly now these reagents will have different energies compared to here, to CO2 and H2O2. So how can you actually then, measure the amount of basically now energy, that's been going around? Well, this is what you do. This is called a change in free energy. So now your reagents will have a different energy compared to your products. And how do you measure that change? How do you measure the change of energy coming from your reagents to your products? Well, you do this following equation, which is very similar, which is delta G is equal to delta H minus T here, it basically. So I'm thankfully pleased to watch this video. So what you do is you take this delta and you put it here. This is a mistake from the book. This is how it's supposed to be. Delta G is equal to delta H minus T delta S. So that's basically how you look at the change of energy. Delta is literally means change. So here is literally this H is basically the delta H. If you want to calculate delta H, delta enthalpy, what you do is actually you take the delta. So you take delta H is literally the enthalpy of your product minus the enthalpy of your reagents. And same thing goes with the delta S, so the entropy. So it's the entropy of your product minus the entropy of your reagents. And you can do the same thing with delta G. So this is one way of looking at delta G, right? Well, there's another way of looking at delta G, and it's basically the following. Just trying to find it. Here you go. So it's literally delta G can also equal G final minus the G initial. So this is the G products minus the G reagents. So hence this is you're measuring the change. What happened when you started off from your reagents to your products? That's what you want to measure. How much did the energy? Because now suddenly you have different bonds. You have different bonds with different energy forms. How's that changed that when this reaction has actually occurred? So you start picturing it's like, okay, why do we want to know this? Why do we want to know this change in free energy? Well, this change of free energy is extremely important to know because it will actually help us predict if chemical reactions will occur. So as we know in life, there's going to be a lot of compounds that are gonna, come together. They're always going to be randomly, uh, touching with what's it called, reacting with each other. But how do we know that these reactants, like these specific molecules, when they come together, they will react or not? We actually look at the delta G. So if the delta G is positive, so this literally means that the product's free energy is much more than the reactant's one. That's what it means. It's positive G. We know that this is endergonic, meaning that this is not going to happen spontaneously. Because think about this: if the products have more energy than the reactants, where the hell are you going to get the energy from to give to your reactants to give your products? You cannot have your products have much more energy than your reactants because you start from your reactants. So by the law of the first dynamics law, you cannot create and you cannot basically destroy energy. Okay, so these are reactants, they have this amount of energy, but our products have much more. But where did that extra energy come from then? So it's not going to happen spontaneously. We need to add that extra energy for this to occur. So if the delta G is positive, then we can know for certain that it's not going to happen spontaneously. You need input of energy for this to happen, for this reaction to happen. If the delta G is negative, meaning that the products have less free energy than the reactants, then this can happen because you have enough energy to go through. So the first law of thermodynamics is basically being abided by because we have enough energy and reactants to create products that have less energy. Perfect. So this can be actually spontaneous, and we call this exergonic reactions. So let's imagine basically let's see this more in a kind of a graph form. So you have here your reactants. So you have the reactants over here. Basically, this is the free energy. So if you see the reactants have way much low energy compared to the products, this is endergonic. So meaning that delta G is higher. Energy has to be supplied because all this energy over here, where the hell are the products getting it from? They're not getting it from the reactants, they're getting it from somewhere else. So hence there has to be an input of energy. So this it cannot happen spontaneously. But if the reactant has much more energy compared to the products, This can happen because now the products are taking this energy from here. So this can happen spontaneously. And of course, energy is released. This extra energy that you don't need is being released. Well, this extra energy over here, we need to supply it to give this products. So this is endergonic and this is exergonic. So then let's talk about something called activation energy. Activation energy is very important because if you think about it, is that if we go here into these exergonic reactions, and let's take an example here with gas. When you put gas into a car, it doesn't spontaneously start, right? We need to spark it up because it's not just gonna be like, okay, let's just all spontaneously start burning. Because if that was true, then we'd be losing gas constantly. We need to basically go into the car and start it, and that spark is what starts this exergonic reactions. So even though they're spontaneous, they need an extra kind of a small little boost of energy. And that's what we call activation energy. Is that extra energy required to destabilize existing bonds and initiate a chemical reaction. So think about this as literally the key of your car. To start the gas to be burned so we can use that into energy, we need the key to start the engine. And the engine, what it does, it just gives an extra energy that destabilizes a bit the bonds in the gas, and that makes it then burn and basically give off a lot of energy. And of course, in these exergonic reactions, their rates, how fast they go, depends on the activation energy. If you need a lot of activation energy, they basically means it's going to be very slow. If you need very low activation energy, it means they're going to go much faster. So hence the rate can be increased here, the rate of a reaction by increasing or lower by increasing or decreasing the activation energy, but also by increasing energy of the reacting molecules by giving heat. So that's two ways. So the first way is increasing energy of reacting molecules. You can do that by heating. The second is lowering activation energy. How can you lower this activation energy, this extra energy required to stabilize bonds? And that is something by you could do that by catalysts. Catalysts, what they do is they actually influence the chemical bonds. These are literally molecules that go into the chemical bonds and they make them a bit destable. So they're reducing now the activation energy suddenly from here to here. So basically, blue is uncatalyzed, so the red is catalyzed. So meaning you put the catalysis. So you're reducing the activation energy because this small energy needed just to destabilize the um, the bonds is already being done by your catalyst. So now you're reducing it. So now basically you can actually you need less energy. But remember, catalysis cannot violate laws of thermodynamics. So these are can be catalysts can be used really well with exergonic, but you cannot use them for endergonic reactions to make them spontaneous because endergonic they need much more energy. Catalysts don't give energy. All they do is reduce the activation energy. That's all they do. They do not give energy, just reduce it. So hence, in an endergonic reaction, which needs free energy, catalyst doesn't do that. Doesn't give it. It just reduces the activation energy, but they still need energy to supply this whole thing. So keep that in mind. So now going on to actually, guys, I'm gonna stop here, and then I'm gonna actually ATP is gonna be a small little video, so not to confuse you guys and not to go too deep. But I will be talking about ATP in my second video.